Hello, this is going to be the practice problem video on topic 8 on Flexure. Today we're going to be doing the test number 8 from 2019, which has a rectangular cross-section, so it's a fair bit easier than the T-beam that we did in the notes last time. So a lot more straightforward than having to draw this cross-section. If you want to challenge like one of these more complicated cross-section ones, then check out the problem just before this, the one from assignment 8 in 2018, which has you deal with an I-beam. So that's kind of fun. This one will be dealing with a more straightforward cross-section again, but more complicated stacking of materials where we actually have 3 materials stacked vertically to make a more complicated compound beam. So this beam extends from z equals 0 to z equals Lz and has 3 different materials depending on what the y parameter is. Then we're going to have gravity affect it in the y direction, the negative y direction, so downward. And then what else do we have? No moments applied. Okay, so just gravity. And then using maple, ignoring shear displacement, plot the y displacement from z equals 0 to Lz and determine the y displacement of the z equals Lz surface, so the far Lz surface. Then using flex, plot the y displacement of the center of the beam in x and y from z equals 0 to Lz, and report the y displacement at the center of the z equals Lz surface of the beam. So what we can do is move this part over so it'll resize when we're in web view and we can see this part of the problem here without having to look at the solution code and get distracted by that. And also we can see our Flexure summary at the end of the notes that has a combination of a bunch of the formulas that we can use to refer to in case we get stuck. All right, so let's get some maple code going for the first part of this. Restart, and we'll say, so you could build it up using the previous code. This is actually pretty similar to the thing that we solved last with that T-beam, but let's forget about that and let's just build it up from scratch and talk about where things come from in here. So it goes from y equals 0 to ly is 0.2. Let's put that in. Ly is equal to 0.2, lx is 0.5, and lz is equal to 4. Then we have a piecewise function for a number of different things, for the Young's modulus, the shear modulus, and the density. And we have gravity affecting it from this density, but if we're not going to be calculating the shear displacement, we won't actually have Poisson's ratio mattering in the maple program. So let's put in E is equal to piecewise. If y is less than 0.2 times Ly, then we've got 70 gigapascals, so 70 E9. Y is less than 0.6 times Ly. I'm getting that from this range over here. Then we've got 130 gigapascals. And if y is greater than 0.6 times Ly, we're going to have 200 gigapascals. Now that we've got that written, we can do something similar for the Poisson's ratio and the density, even though we don't actually need the Poisson's ratio one, in case we want to do a check with shear later and see if that's responsible for some of the difference. It's easy enough to put it in. So we'll put in 0.35, so 0.3, 0.35, and 0.28. And then for the density, 4,000, 6,000, and a lighter material, 2,300. Okay, so here's our material parameters put into this thing. Because we have a beam which is extending in Z, we can actually use the same free body diagram that we had in this situation, except with no moment on the end of it. So we'll take a, let's make a new, actually I guess we'll need a bit more than that. So we'll paste this in here, and we'll get rid of this moment on the end of this beam. We have an XY cross-section, and it's extending in Z, so we can, let's do this way. Control-Shift-N to put in a new layer, paste that in there, and now we can just select and delete instead of having to draw rectangles, which I guess is a little bit nicer. Yeah, and Great, so there's that free body diagram. What else can we do? We can show the internal slice at some point, and that will be there with internal shear force and bending moment. So let's draw the shear force in red. We can get a little bit of a thinner line there. Sure, 4. And put / to put on an arrow, and this is going to be V. Yeah, that seems fine. And then a bending moment. How about blue? Why not? So internal bending moment will be in that direction by default for its sign convention. May not actually end up being in that direction, but let's just draw it like that. So this is the set of internal forces and moments for the particular problem that we're solving here. Okay. So we'll set that up and then resize it so we can see everything all at the same time. So as before, there's a couple of different ways that we could do this. We could do the statics approach, where we say use the classic way that we would deal with this before, first finding out the distributed load by saying that rho is going to be an integral over the cross-section. Well, if we integrate rho over the cross-section, that is, we can find a mass density, linear mass density, which is the integral of rho with respect to area. So how are we going to integrate with respect to area? We're going to multiply by the width, and the width is just a constant Lz. So we'll take the width times rho from y is 0 to Ly, and then we'll divide that by, well, nothing actually. So why nothing? We've taken our density, which is our mass per cubic meter, mass per volume, and we've multiplied that by the area, a little bit of area element, and then added it all up across the cross-section. That's what the integral does. We've multiplied it by the width. It doesn't change in z. Otherwise, we'd have to do two different integrals there. If it was like a piecewise function that depended on y and z, then we would have to do a two-dimensional integral. But in this situation, we can just integrate across y by multiplying by the width. All right. So now we've got the linear mass density, and to find out the distributed load, we need to take this linear mass density and multiply it by the weight. But first, we should probably check that we did that correctly. So the cross-sectional area of this is 0.2 meters times 0.5 meters, which would be 0.1 meters squared. And when you take 0.1 meters squared and multiply by densities that are on the order of thousands, you should get a combined density, which is on the order of hundreds. But we don't. We get a thousands density. And the reason is we actually messed up what the width was. So the cross-section of this is not z times y. It's actually supposed to be x times y. So that means we need to make the width not Lz, but Lx. And now we've got a much more reasonable mass density and can use that to get the distributed load. So P naught distributed load is equal to mu times 9.81 meters per second squared. And this is directed in the downward direction. So that's the direction that the distributed load is going to be acting on this problem. Now we can work out what that is. It'll just be 10 times this mass density, and then we can probably get rid of a lot of the things we were reporting before. So we don't need to see the output from these. That's just going to be clogging up our output area and limiting what we can actually see. So let's do the statics approach next. On this thing, we've got no net force, solve Ry minus the integral of P naught from z is 0 to Lz. And we've got, so that's the net force equation. We've got a net torque equation about the left-hand side, which is going to be, let's sum the torque out of the page just because that's kind of what we're used to. So we'll say Rm is out of the page there. It's in the negative x direction. And we've got another torque, which is from this P naught along the length, integral of z times P naught. Z is 0 to Lz. All right, so that should be giving us what Rm and Ry are. And we need both of these to be positive to counteract this weight force. So indeed, they are. That seems good. The beam is kind of long in meters, right? If it was 2 meters, then you would expect that Rm and Ry would be numerically about the same, right? Because then the equivalent point of this distributed load is at 1 meter out, so you'd have the same reaction force as you would reaction moment. But for a 4 meter beam, you have a moment which ought to be around, or exactly, twice as big as the reaction force. So that is indeed what we get, and everything in the universe seems like it makes sense. Next up, what we'll do is we'll use this internal diagram, this internal shear force and bending moment diagram, to figure out what that internal shear force is. And V has to equal Ry minus the integral of P naught from Z is 0 to Z. And the moment will then be it'll be negative Rm, because Rm is spinning this in the same way as that moment, negative Rm plus the integral of V from Z is 0 to Z. And let's plot those just to check what we get. We need them both to go to 0 at the end. And everything seems like it's making sense. We've got a negative internal moment because of this one applied by the wall, and we've got a shear force which is starting up quite high to counteract the wall's effect and then dropping down gradually as we move along. So to calculate the displacement that comes from this according to bending, what we're going to need to do is first find the flexural rigidity, and we can get that by integrating. I guess we'll put this below the width formula. EI is going to be the integral over the cross-section. So integral of W times what? Integral of y minus y bar squared, but we're going to weight this integral with the stiffness. And integrating over the cross-section means multiplying by this width, which we can do because nothing depends on the x position, and then taking y from 0 to Ly in this case to go over the whole cross-section. But that's not going to work because we haven't put in what y bar is, so we need to figure that out as well. And y bar is the weighted average y position, where the weight is the stiffness. So we're going to take the integral of y times e times w from y is 0 to Ly. The times w and the integrating from 0 to Ly is just to go over the cross-sectional area, and then divide that by the integral of e times w, y is 0 to Ly. So this is an average y position over that cross-section. Now where do we think this will be? Looking at this shape, if we had the same Young's modulus everywhere, we would expect that y bar would be just the one right in the middle, right? We'd expect that this would be at Ly over 2, which would be 0.1. But we have a higher Young's modulus near the top of this thing, so it's going to be pushing the average, the weighted average y position towards the top. So it should be above 0.1, closer towards 0.2 somewhat. Yeah, a little bit. So a little bit above 0.1, getting us up there above the center. All right, now we've got our flexural rigidity calculated, and with that, we can use the internal moment to figure out what the curvature is locally. So the curvature is going to be the moment over the flexural rigidity, and then the curvature can be integrated to find out what V is. So the displacement from bending is going to be equal to the integral of C, well really two integrals, integral of C from x is 0 to x, and then integrate, not x, sorry, z. From z is 0 to z, and then integrate that again from z is 0 to z. And once we've got those two integrals done, so this is two integrals with respect to z, notice that it has actually done things correctly for a fixed support. Really, we integrate once and get the slope at each point, but the slope is supposed to be 0 at the end because of that fixed support. So we end up with a correct thing that has no slope at the left end and no displacement at the left end. Now we can check this method by using the beam equation. So let's go to our summary of stuff that's going on here and see if we can work out how that works. Rather than doing this approach to figure out the displacement, we could instead say desolve, let's say beam equation check, desolve the differential equation that negative P naught is equal to EI times the fourth derivative of V at Z with respect to Z. And we're going to solve that subject to the boundary conditions that we have for a beam that is fixed on the left end and free on the right end. Now, when it's fixed on the left end, that tells us that at the left end, there can't be any displacement or angle. So that says V at 0 is equal to 0, and D of V at 0 is also equal to 0. At the right-hand end, we've got that there's a free end, and that means there can't be any shear force, any third derivative, or any moment applied. So at the right-hand end, D 111 third derivative of V at LZ is equal to 0, and the moment is 0. Second derivative of V at LZ equals 0. The moment and shear are not exactly the second and third derivatives. They're the second derivative of V times EI and the third derivative of V times EI times flexural rigidity. But if you know that the moment and shear are 0 and the flexural rigidity is not, then this tells you that the second and third derivatives have to be 0 directly. All right, so now we can try to desolve that and see if we get the same values as before. Apparently we don't. Ambiguous input, the variables z cannot appear both in the functions and the system. I wonder what I did wrong here. So let's see. We said P naught. P naught is just a thing. It doesn't depend on where we're at with respect to z. We've got a fourth derivative of V at Z. And now did I put V for each of these? V at 0 is 0. And, you know what? It's because we'd already assigned what V was. So I have a feeling that this would work fine if we put it above where we did this static stuff and had already assigned what the variable V meant. Yeah, so there we go. We've got this thing figured out for V, and we can, let's see, how do we work that out? Maybe eval mod. Right. So we've got the same numbers, hopefully. Yeah, exactly the same coefficients for the z to the 4 term and the z cubed term and the z squared term. So using the beam equation, perhaps more directly, we can replace all this stuff that we were doing with statics, sort of. We would then have to go in and define what V and what the shear force in the moment were, but this is a totally fine approach to solve the problem as well if you don't want to do the statics approach. So the next thing is to build this up in FlexPDE and get a check of this. Oh, actually, I suppose we can also find out what the displacement is at the z equals LZ surface. And to do that, we'll just say subs z equals LZ into V and call this V tip bending. Doesn't matter which of the V's we used because it's the same thing, so we're just going to use the one we assigned from statics earlier. So V tip bending looks like it's 3 millimeters down is how much this beam has bent under its own weight after 1 meter. That's a lot more than the T-beam we were dealing with before. And why would that be? Well, the beam is not nearly as big in Y as the other one was, but it is quite long. It's 4 meters long, and it's not made of stuff that's as stiff as tungsten. Not quite. I mean, the top part of this is pretty stiff, but it's not as thick and not quite as stiff as the tungsten. So we end up with a larger displacement than we had before. So let's build this up in FlexPDE. I've saved this as a new file. We've got the name different. Now let's just change it to topic 8, practice, maybe 2019 test 8. Sure. Okay. So what do we need? We don't need this stuff. We're going to put back in our Lx is 0.5 and Ly is 0.2. I looked at the maple, but that's kind of a mistake. I should ignore the maple and go back to the practice problem in case I typed out something of the question wrong. And this way I'll be able to catch the error. Okay, and Lz is 4, so 0.2, 0.5, yeah. And now we've got the material parameters. How are we going to put these in? Well, we're going to say that if y is less than 0.2 times Ly, then 70 E9. How do we deal with the next one? Well, just like in programming languages generally, rather than just else, we're going to say else if. Yeah? Else if y is less than 0.6 times Ly, then the next condition, 130 E9, and now we can just use an else. Else 200 E9, and that's it. That's the new information for how to deal with 3 different layers instead of 2. In our maple code, we didn't actually need the Poisson's ratio. We could comment that out and we get exactly the same stuff. But in FlexPDE, it is relevant because that's the axis coupling still matters for this system. And without the Poisson's ratio, the shear would take over and just slide this stuff one plane to the next quite a lot and make the object kind of disappear into oblivion there. So we don't want that. We want the object to stick around. So let's put in the Poisson's ratio rather than just leaving it as 0. So 0.3, 0.35, and 0.28. And the last one is the density. We've got 4,000, 6,000, and 2,300. Okay, that's all good. Next thing, we need the bottom and Z to be fixed. Yes, that's right. And the top surface, we're going to have no load this time because we don't have a moment applied to it. So we'll get rid of that thing we were doing before. And now for the structure, let's go with start at 0, 0, line 2, LX 0 to LX LY to 0 LY to close. So that's just drawing a rectangle without specifying any different boundary conditions on any of the sides, because conveniently in this situation, all the sides in the XY plane are just free along the length of the beam. We do have this distributed load on the top, and we could pause this and break it up on the top to apply that, but rather than doing that, we can just leave it with the example code where we said minus 9.81 times the density, and so minus G 9.81 newtons per kilogram times the density is the per unit volume weight of this thing. So we don't need to turn that into a distributed load and apply it on the top. It's actually better to have it as a volumetric load anyway, and it's easier to do that. So there we go. Let's see, what else are we going to do? We're going to report the value of the displacement at the end, and I think that's it. Here's our beam. There's the beam bending, and the displacement at the end is the same as we got in maple. All right, so that's it. We got it solved. That's all the question actually asks us to do. If we wanted to, we could see what if the shear is responsible for this extra bit of displacement that we're seeing, that we're not seeing in FlexPDE, or if that's more to do with the boundary conditions. So let's try getting rid of the boundaries on the side. What can we do? We can get rid of not the Z boundary, that'll allow it to rotate. We can get rid of the X boundary. This is allowing it to flex out a little bit on that surface, and this makes it move just slightly more and gets us a fair bit closer to what's going on in the tip displacement there. What about the shear deformation? So that would actually make things slightly worse. We still have a bit of coupling of stress in the vertical direction, making it a little bit stiffer at the wall than we would like it to be. We could try increasing the grid density, forcing it to try to use more elements, and see if that makes a difference. Oftentimes it's better to just let Flex do whatever it wants with that grid density than to try to force it. So now it's going to put elements where it thinks it needs it, and that ends up with more precision around the anchor. So another thing that we could do again is add in the shear and see if that makes much of a difference. So let's work out how the shear works. We can say that G is equal to E over 2 times 1 plus nu. And because the Poisson's ratio in E is changing across the length, we're going to want to figure out what the average G is using the regular averaging that we were doing before. So this is going to be the integral of W times G from y is 0 to Ly over the integral of W over the area, right? And let's figure out what that is. That is the integral of W from y is 0 to Ly. So we are finding the cross-sectional area explicitly now. We know that it should be 0.1. And I forgot a bracket there. Yeah. And we need that when we're going to be finding out, to find out what the shear stress is. So from the V that we discovered, we can say that tau on Z in the Y would be equal to negative V, because V was sort of directed pointing down, so it would match up with the moment we were applying in the right direction. So negative V over that cross-sectional area. And then we can figure out what the shear strain is by taking tau ZY. Local shear strain is going to be, so G ZY is equal to tau ZY divided by the shear modulus. Let's use the average shear modulus. Then we can find the shear displacement by taking an integral of GZY from Z is 0 to Z. Okay, and then find V tip shear by substituting Z equals LZ into V shear. Let's see. So it says that the tip displacement from shear should be a relatively small correction, only about 5.8 microns. So it really doesn't add much to what's going on here, and explain much about the difference. So most of this difference then is either the numerical error in FlexPDE or the large displacement bending, the small angle stuff that we're skipping when we do this beam equation in Maple, or the anchors. And it seems like the anchor is responsible for most of the small discrepancy. But it's not much of a discrepancy, and that's why the answer is still very close to the thing that we calculated here. Okay, so that's it. Thanks for watching, and I'll see you next time.